So we're heading into the home stretch of our discussion on Java parallel streams internals, and we're going to wrap up talking about non-concurrent and concurrent collectors, which are really important to understand. They're really fun to understand also. And we're going to talk about kind of the key behaviors and the key differences in behavior between non-concurrent and concurrent collectors. So first, just a quick recap of what is a collector. A collector is an interface in the Java streams framework whose implementations can accumulate input elements in a stream into a mutable result container, which often is a collection, but as we've seen, could also be a string and some other data types as well. Collector implementations can be characterized in various ways. There are different characteristics they can have. They could be unordered. They can have this thing called identity finish. They could be concurrent. And so we're going to focus here on the difference between concurrent and non-concurrent, because that's one of the important characteristics. The distinction about whether a collector is concurrent or not is really only relevant for parallel streams, not for sequential streams. You could also have a concurrent collector and a sequential stream, but boy, would that be dumb, because you're going to be wasting your time with all this extra overhead for no good reason, because there's only one thread of control. So it's really important for parallel streams to have concurrent versus non-concurrent collectors, or to understand the difference. Now, the other thing to remember, and this is a little confusing because of the terminology, a so-called non-concurrent collector can be used quite faithfully and correctly in either a sequential stream or a parallel stream. It's like the famous Saturday Night Live skit about the Shimmer non-dairy floor wax, which was touted by Chevy Chase as being both a dessert topping and a floor wax. And if you ever want to go back and watch that, it's on YouTube. It's pretty funny. So let's talk about the structure and functionality of non-concurrent collectors first, and then we'll talk about structure and functionality for concurrent collectors. So a non-concurrent collector works by merging subresults together. Where do those subresults come from? Well, let's take a look. So recall how things work with Java streams in general, especially parallel streams in particular. We start by taking the input and we partition the input up into chunks, and then we hand those chunks off to the threads, the worker threads in the common fork join pool, and they run, do their thing, and then after they're finished, then those are collected into intermediate mutable result containers, such as a list of some kind, or a set of some kind, or a map of some kind, or a whatever of some kind. So you'll have a bunch of these things for each of the subresults. And keep in mind that the different threads that are in the worker pool for the fork join pool will operate on different instances of intermediate result containers. So there could actually be quite a number of these intermediate result containers that are being worked on. And then as we kind of back out of the recursion, these subresults are merged together, pairwise, culminating in a single mutable result container that contains all the results that have been merged together. And as we talked about before, that's where you can get into some trouble in some situations. However, from a concurrency point of view, you're all fine, because only one thread at a time in the fork join pool is ever used to merge any given pair of intermediate subresults. So there's no need for locking and so on. So that's good. That simplifies your life. So the good news is that this process is thread safe. This process is order preserving. However, it can be costly for containers like maps and sets. And that's because they are expensive to merge, because unlike a list, as we talked about before, we just tack one list at the end of the other, with the sets and maps, you actually have to go through and take each element from the set or map and then merge it into a new set or map. And that takes time. It typically would take, it depends on the set or map that you're using, but if you're using a tree set, for example, that could take essentially, n times log n. So it could take n log n time to do the merge, because you're putting n elements into a tree set, which uses binary search, which will take log n time, on average for each insertion. So therefore, it could take n log n time. If you use a hash set, you might take less time, but then you're kind of at the mercy of how that's implemented. But the good news is Java's pretty clever about how that works. However, it still takes time. So given that quick overview of non-concurrent collectors, let's go ahead and talk about concurrent collectors. So a concurrent collector creates one and only one, there can be only one mutable result container, and accumulates all the elements into it from the multiple threads that are running in parallel as part of the common fork join pool. So there's only one mutable result container, and it has to be a special kind. So as usual, just like we did with the non-concurrent collectors, the input is partitioned up into chunks. That doesn't change because we're doing parallel streams. Each chunk runs in parallel in the common fork join pool. That does not change. However, what does change is that these subresults, as they're finished, are simply added directly to the concurrent result container, the one and only concurrent result container. Now, that obviously has a big implication. That collection must be a concurrent collection, or another way to say it, it has to be thread safe. And all the different threads that are running in a parallel stream, of course coming out of the common fork join pool, share a single concurrent result container, and they're just putting stuff directly into that. So one of the nice things about this is that there's no need to merge any intermediate subresults because they're just going directly into the mutable result container. The downside, of course, is that if encounter order is important, it's not preserved, and you need to have collections that are synchronized properly. So when is concurrent collection a win? When are concurrent collectors beneficial relative to non-concurrent collectors? Well, that's actually quite easy to think through because it's going to be the situation where the concurrent collector will outperform or may outperform a non-concurrent collector if the merging or combining costs are higher than the synchronization costs. So remember, concurrent collectors don't require synchronization. Concurrent collectors require synchronization and don't require merging. Non-concurrent collectors require merging but not synchronization. So if synchronization costs are very, very low relative to merging costs, then a concurrent collector could be a win. And we'll actually quantify that here shortly. And it all depends on the typical n times q model we've talked about before. As n gets bigger, as you might suspect, the win gets bigger for using a concurrent collector. Now, the really clever way to do this is to use concurrent collections that are intentionally designed to work efficiently and scalably and optimally in heavily multi-threaded environments or multi-core environments. And a great example of this, of course, would be a concurrent hash map. And you can take a look at this article that talks about hash map versus synchronized map versus concurrent hash map. And of course, a classic hash map has no locks whatsoever, so you would never be able to use it as a concurrent collection unless you manually put locks in there. There's also something called a synchronized map, which has a single lock. And then there's something called a concurrent hash map, which has a separate lock for every one of the elements in its hash table. So every hash table element has its own synchronization mechanism using something called compare and swap synchronizers. Very, very cool technique. And so it's very, very, very scalable. And the reason why it's much more scalable is unlike a synchronized map where there's one lock which quickly becomes a point of contention, a concurrent hash map has separate locks for each of the different buckets in its hash table. So it scales up much, much better. And I've actually, of course, got an example to demonstrate the performance benefits of using concurrent hash map versus synchronized hash map, which we may or may not have time to talk about. Okay, so that's an overview of non-concurrent versus concurrent collectors.